Hello, hello. О!
Okay. Good.
Machine. This is fine, this is fine. And where are my students?
So I have a question. Task number 3.
Yeah.
Is it okay just to do it without using Scilab, like solving direct using Laplace transform?
It's in
I mean,
which environment?
task number 3.
Yeah, but inside which environment? Originally it's intended for what? For something like this. And you think what kind of environment?
No, I look at the circuit itself. I think it can be solved.
It can be solved.
But if you want me, or can speak for myself, to use Scilab, I think I can manage this. I have very little knowledge about it. So.
You know, I'm planning next lecture to solve it with.
Okay, if you can do that, then I really appreciate it.
Yeah, I can. I will show you how it's done.
That would be nice.
Mm-hmm. Tiny probe. My tiny probe.
Okay, nice. Please,
I think I will be able to do it. Yeah. Now it's time. today on my plan measuring instruments. What's on my plan? How can we perform some measurements? And what are errors? Oh. What about measurements? Okay, where's my... Oh. Sometimes it's good to know what's this, how many volts, amps, or what. This is my build. Oh, axon wire. The axon wire system measurement. Come close. Oh. Here is my first example. It's the axon wire system. Maybe one more example. Where is my hand? Oh. This nice example, compass and a coil. If we open old book about measurements, we will find two main classes, moving coil and moving iron. Huh? Axon wire system, like this one, is a moving coil. This one pure moving coil. More. This one. What do we see? Magnet and a moving coil. Coil inside magnetic field. No, this one has a very small coil. Iron. Hop. And there. Which one? Okay. Wait, oh. This one. School. Demo from school. Closer. Moving coil. This one is a moving coil system. Something familiar? You had like this in school? No? Oh. Maybe I have read it. What's the idea behind moving coil system? Oops. You have magnet. You have coil inside magnetic field. Spring is attached to return coil to zero. And some kind of index. Let's say it turns to angle of magnet. Here should be coil. And on. Wait, on. Here, coil and the index. General. If we have, let's say, let's assume it's a frame. Something like this. Frame. Rectangular coil inside magnetic field. If current flows, we will see a rotating moment. It will try to rotate. This moment, let's say moment from current, can be expressed like induction multiplied by length multiplied by A, where A is a width and L is a height, multiplied by number of turns and multiplied by current. Or it can be written induction area of this coil multiplied by number of turns inside the coil and multiplied by current. Here, if we take, for example, this teaching aid, we have a spring. Spring like this, returning to zero. For such kind of spring, moment of spring is W, which is stiffness constant of the spring, multiplied by length of turn off. If current flows and we have some reading, not like here, it's showing something all the time because was in students' hands. If we have some reading, moment of current equals of moment from string if it's stable. Even if it shows zero. So this means what? Alpha equals to BSVE. So alpha here is what? BSV small v number of turn, large v is the stiffness constant divided by current, or meteorological constant current. Fine, it's what you will read in old books on measurements. You got electrical measurements, something.
What is alpha? Differential?
Huh? Yeah. And it shows, it should be written in amperes, but alpha is deflection from the zero, from the neutral state, or no current state. Something like this. You have metrology course, something like this. Electrical measurements.
Not yet.
Here in in your schools? Nothing. What I'm doing here? Okay, what does this mean? I have a very nice formula. What? Angle is proportional to current. It's DC measurement. What will happen if I use non-DC? If I apply something non-stationary. So, current moment is P as number of turn E. Yeah? If current is actually a function of time, current moment will be the same as V, because all this is current independent from time. Now deeper. Where is my why? I would like to show one thing. What I need to adjust my generator. Zero. Can I, for example, switch my... Okay. Come on, I need this. Look at him. Low frequency sine. You can see it follows.
Why is it oscillating?
Huh?
Why is it oscillating?
Because it's AC plus minus, and moment follows. Wait one moment. Very low frequency. Very low frequency. You can track this. I got a very low frequency signal. But what will happen when I increase frequency? Watch here. I'm increasing frequency. frequency. See, it's happy to fall. Frequency increases. Oh, 0. I decrease frequency. Falls. Yeah. I increase frequency and shows 0. What's this and why? Why it shows 0? Idea, the system itself has inertia, mechanical inertia. On a small frequency, it follows, but there is a border or critical frequency when oscillations are too fast to follow, and this thing became what? Inert mass, it integrates. I will use this camera. So it became, I have a signal there. Yeah. Here it is. I have a signal, but it's only tiny vibration, what I observe. Here, off, if I have periodic signal, so if current is periodic, I will get alpha as average 1 meteorological constant time. If non-periodic, alpha will be again a meteorological constant from 0 to time. E times d time. You can use such kind of measurement instrument as mechanical, electromechanical integrator. I work this box. If I open it, you can see acceptance sheet. It's dated 12th of December 1943. 1943. Inside is a beast called ballistic galvanometer. By design, it's an Arson-Wall system. The Weston system, the coil is sitting on the two bearings. Weston system works in any direction, and the Arson-Wall system, the coil is suspended on a flat spring. Here I have Arson-Wall system. Ballistic galvanometer needs low mechanical moment as possible, but it has behind this coil, it has additional weights, two small weights, to make its inertia calibrate. It has a period of 45 seconds. I'm not 100% sure, but people believe that this thing was used to detect German submarines in breaking coastal defense. Coils were placed on a straits. If submarine, steel and magnetized submarine, passes the coil, magnetic conductivity of environment change and integrated it can be detected. They all are earliest I see 1938, last one 1944. They are all accepted by the government. They all government made. Here is acceptance sign. So here this thing is ballistic galvanometer instrument. If we integrate induced EMF, we will get flux. Yeah. To your attendance, Cambridge flux meter. Moving coil instrument, width increased, inertia. Here. Cambridge flux meter. Comes with calibrated coil. If you move this coil through a magnetic field, it will integrate not possible to measure here. Okay, it will show you interval from 0 to time of induction passed through this coil. So this will give you magnetic flux. Yeah. But what if this Hartmann and Brown in its glory day was one of the top range. And it's marked as AC. Yeah, it's a C sign. How can I buy this nice measuring instrument from Hartmann and Brown if half is an average? Okay. Answer is, what can be answered? Rectifier. The answer is rectifier. can be one design has something like this. It's one version, another version, full I should draw like this. Another version is with the full bridge. What will show instrument of such design in reality? For the first version, current through instrument will be something like this. Okay. If as I draw, I should draw like this. P double P. So alpha will be meteorological constant divided by double P, integral from 0 to P. For the this for such kind. For the second one, we will see something like this, and alpha will be meteorological constant divided by double P, integral from 0 to P, time, plus from P to double P, with, sorry, not plus, but with the minus sign. That's what it shows in reality. I would like to show you something. But before I can show you something, I need to tell what is something. I have assembled one trick network. Here, you know this device. It's a generator with harmonics. My trick network, one moment. Ground. Battery. Ground. My generator. And this is my voltage. See what I got? This circuit allows me to set DC offset plus 12 volts. Here I have my complex signal from my generator. With the help of transformer, the signal will be summed with DC offset. I need this because this generator don't have C0. Fourier role has DC component plus of A power or, if you want, cosine K double P time plus SK sine one DC component and multiple AC component. To create DC component, I need this offset circuit. And I will disconnect this. I will connect this. I have nice, let's say, 15 volts. One moment. I will adjust my camera first. This way. Yeah. Small 15 volts and here 15 volts. One moment, I will. Yes, we need. Here, we need the scale. You can see it's small digits, 15 volts, 14, second scale. 15 volts RMS. This one pretends to show MS. It's a big problem. Actually, angle proportional to the what? To the average of absolute value. And here, volts AC pretends to be RMS. Let's at this moment. When my voltage is fine, everything fine. 15 and 15. What? Not so easy. Let's say something ground. 16 volts, I think will be okay. Here, 16 volts. RMS of the signal contained in third harmonic is 16 volts. Let's I'm changing only angle of the third harmonic. Do I change amount of energy flowing from generator? No. Amount of energy remains the same. This means what RMS should remain the same. But what happen with my instrument? Calibrating manufacture. Did what? They put RMS digits on the average of. So this scale is true only for pure sine. Presence of the first harmonics, I gave what? 1/2, 50%. From 12 volts, I will set be around effective value is 16. In this position, 16.5 mean is 13. So 3 volts. Okay, let's try it with not third, but with the second harmonic. Effective is 16, 14, 15, 2 volts less. It's more sensitive to the first harmonic. Small sensitivity to fifth harmonic change a little. It's now step 1 and 2. And what about this component? Let's check reaction to this component. Maybe I will change something wrong, for example. Here, 16 volts. Exactly. 16? Now let's apply the component. Effective is 20 volts. Or still 18. On in opposite direction. Okay, 18.3 here, 19.3, 18. Not good. So this instrument shows true only when voltage is pure sine. Okay, I can take another one. Maybe this also. Should be 16 volts. Show something. With addition of third. You see what I see? Is it reliable? I don't think so. In case we deal with the presence of the first harmonic, this instrument will not be reliable. What about moving coil? Some one of the moving coil models. Moving coil. Not moving coil, but moving iron. Old moving iron instrument. See what happened when I connected it? Do you see the form of signal? It's so hard. Put so hard burden on my generator. I'm forced to reduce voltage. And what about harmonics? More reduction is needed. No change. It's immune to harmonics. To the third. And what about second? Stand still. So see, moving iron shows real RMS within its frequency range. But it heavily loads signal. It puts a heavy burden on the circuit under measurement. What else? Any more old instruments?
Do you have any sense?
First we need the dynamo moment. And then we can speak on thermal sensor. Dynamometer. Usually it's a system for what? For power measurements. Metric system. Usually when we speak on dynamometric system, it's a wattmeter. It's a coil inside here in the coil. It's a coil inside here pair of coils and inside yellow coil, inside pair of black coils, dynamometric system coil, inside the coil. This one. No, you can see internal coil. Let's check what's inside the box. And inside is one of my favorites. It's a Cambridge dynamometer. One moment. Volts, something like this, and let's try it with the let's try it with the non-harmonic. See, nothing changed. Same. Nothing changed. Dynamometric system is immune. It shows true, but they in the quality they were most expensive. It's a cadre of the measurement system. It's an expensive thing. What else? Let me bring next one. When you don't understand what happens, best measurement tool you can get will be dynamometer. What's market? Ministry of Supplies. They are available on the market. Next one. This baby. Made in neighboring Estonia. Actually, it's a moving coil. But it's an amplifier. Idea is to make first range wider, but the key moment to make frequency range wider. Okay, what I got 15. 1 second, I will set some ground. 15 volts shows us 15. What will be the effect of the harmonics? We use 215. Here, 15 volts shows us 15. Quite good on the third harmonic, about 1 second. Yeah. Internal. Just 15 volts. Yeah. It was 15 volts. Swings from from 17 to 15. So up to 12. So plus minus 5 volts. Swings if I change angle of the second harmonic. Oh. Not very bad, but yeah. This instrument has problem. Simple attempt to make wide range instrument reads high in resistance. But it's not so one. Once this was one of the best in its class. Very good. Okay, not the best one, but good attempt to create an AC voltmeter. I need what's here? Oh. I need a special connector. Wide frequency up to megahertz. And attempt was made to create yeah. 17 volts, maybe more. 20. On AC, everything's okay. Now let's add third harmonic. Real effective is real MS 20. What happens? 22, 18, 22. This instrument has an analog circuit approximately effective value. It's done to make scale nice and linear. Result, see, not very fast. It is not immune to the third harmonic. And what about second? This is disaster. Look what happens with the second. From 15 to 25. 10 volts is an amplitude. How it reacts to the second harmonic. It's a disaster. This interpolating network really works again. And what about the C component? We ignore this C component. This old instrument with amplifier have tendency to ignore the C component. So it's only good as indicator. We have voltage. We don't have voltage. Actually, what's good in it is very low consumption from the network organization. But precision is question. Okay, what showing you can say, come on, stop showing us your museum. Show us something new. Something digital. It's your museum. Let's bring something digital. One moment. I have this. It's an early. Zero. What a nice cement. $18 volts. 17.99. I think it's true. In its word, it's very precise instrument. But what about harmonic? Oh no, 16. 20. And what about second? Should be 22. 21. Should be 22. 21. 19. What do we see? Measurement part is good, is precise, but internal, it's not the same way, and this Hartman and Brown. It measures amplitude of average. Nothing changed. 19 instead of 22. Yeah, on ideal side, 18. It's digital, but it's not an RMS voltmeter. This voltmeter shows us true measurement only when we consider or deal with ideal harmonic signal. More voltmeters for the cut of voltmeters. This one. Students voltmeter. Cheap. Yeah. Let's try. Sixteen. 21. Not ideal. When 19. Oh. 16.1 up to 21 and should be 20. I don't think it's the best voltmeter in the world, but let's check if it's with second component. 23 or 3, 4, 34. And in opposite direction should be 21, shows only 6.4. What can we tell about it? Diagnosis. This thing has an ABC converter for only positive way. This one is worst of them all. Look at him. 32 instead of 23. 6.4 instead of 21. Mistakes. It's not good. So the student's fault method is nothing close to RMS. It has only ADCE or ADC only for positive rate. Okay, we need more methods. Can we try this one? It pretends to be true RMS. Let's check it. Twenty. Yes. Third harmonic test. Pass. Second harmonic. 20.55. True. And what about the C component? Do not react. So it's true RMS on AC, but ignore the C component. I need actually it has a special mode. No, it's AC. Yeah. This one has a special mode. Should be 21, 21.27. Something near 21.2, 21.3, so something near. Only with activation of special mode, this account DC component. By default, no. But this one goes to the good side. It's really RMS. These digital instruments we showed before are not RMS, but something. They are indicated. bench type instrument. 18.3, here 18.4 possible. What about harmonic? Should be 20, 20.3, 20.7, 20.3, 20.8 to 7. So there is bit difference, but appears to work fine. Second harmonic. $22.6. It's good. And what about the C component? What is C component? No reaction. Yes. Again, only with the help of special no. AC plus DC. $22.9 should be 22.2, it's okay. 22.1, big difference, but it something works. So this one appears to be an RMS. It's good one. Can I get it? But on it's default, it ignores the C component. It was high grade instrument. This one is low grade instrument. It's for originally it was in a tool set for it was in a tool set for checking of acoustic system. 1949. Yeah. 15 volts. Maybe it's less. 10 volts. 10 volts and 10 volts. Fine. Yes, reactions observed. Should be. Calculate. 10 volts and drops down to 8. Second. One moment. Effective is 10 volts. 12 volts difference. What can we say? It's not the volts measurement, it's just indicating. We have voltage or not? One more, but it's behind. Very much. Oh, time.
Stop it.
So, what kind of conclusion can we make? We saw different kind of measuring instruments, and only part of them showed us truth. Moving coil shows average. Moving iron shows RMS but towards network and has limited frequency range. All kind of moving coil with amplifier only precise on a signal which they are calibrated. Dynamometer, yes, fine. Digital, no guarantees. Only bearing mark of true RMS showed us something reliable. Simple models, no. Simple models fail. So in any case you doubting what you see, what should you do? Take a scope and check what's the real nature of your signal. Okay. Why I don't see? Because it's nothing. Okay, I need what I need. Time is above me.